Hello to another lecture in this course. So today we'll look at some basic calculus with the complex derivative. This is subsection 221 in the book. All right, so yeah, let's do through some very basic calculus. So first, let's solve a differential equation. So this is the first differential equation that you always want to solve, and it's actually surprisingly useful. It turns out. So suppose you're in a domain. So it's important here, an open and connected set, right? And you have a holomorphic function, and let's suppose that the derivative is 0 for all z. Then f is a constant, right? Now, why is it important for it to be connected? Well, I mean, it is kind of constant if it's disconnected, but you could get different constants in different components, right? So, all right, what is the proof? Well, the proof is just you use the standard result. It's the standard result already says, for differentiable functions from R2 to R2, right? I mean, if the complex derivative is 0, then the real derivative is 0, and if the real derivative is 0, then the function is actually constant, right? So that just follows immediately. Let's look at the chain rule. So if we have two functions, f and g, right, complex valued functions of a complex variable, and f goes from u to v, where u and v are some open sets. So f goes from u to v and g goes from v to c. That means I can plug f into g. So g composes f is a well-defined thing, right? And let's suppose that f is differentiable at z and g is differentiable at f of z, right? Wherever z went. Then the composition is differentiable at that z, right? And the derivative of the composition is equal to, well, exactly what you'd expect from just basic calculus. All right. So we give two proofs because one is an adaptation of the proof from the one variable result, and it's useful to see these, how that works, and it's just it works without sort of referencing anything about differential functions of several variables. But then we give another proof, which uses the several variable version, and then both are actually useful. Both are useful to know. All right, so let's look at the first proof. So this is the sort of the basic proof, the adaptation of the one variable result, one real variable result. So let's suppose that h is a non-zero number. It's going to be a small number, right? That's going to be in our difference quotient, and let k be the change in f, right? So h is really going to be the change in z, and k is going to be the change in f. And first assume that k is not 0, right? So if we look at this difference quotient for the composition, well, what we do is first I just plug these things in here, right? But then what I do is I basically divide and multiply by k, right? This is what k is, right? And I can do that because k is not 0. And so I have this. Well, here I substitute for k. Over here, I note that f of z plus h is really f of z plus k. That's just how k was. That's just how k was defined. So a differentiable function, right, is continuous, right? So therefore, this thing goes to 0. That's the k as h goes to 0, right? Because f is continuous, right? So we have that as h goes to 0, also k goes to 0. And so now we have basically the right thing. We have the difference quotient over here for g at f of z, and the difference quotient over here for f at z, right? And now let's handle this. What happens when k is 0? So when can k equals 0 happen, right? I mean that happens for small non-zero h. Basically, that can only happen if the derivative of f is actually 0, right? So that's the only time that you could, for small enough h, have sometimes k be equal to 0. Well, so for those h's, you just look at this difference quotient and you notice that it's 0, right? And so either way, either if k is non-zero or if k is 0, the whole thing is supposed to be 0. Because, if k is non-zero, well, then this thing is going to 0, right? So it's not a, that's not a big problem. I just can't do this division if that was 0, right? And so, again, multiplication is continuous. We can take this limit, as h goes to 0, so then k will go to 0. And so this will go to the limit of the g prime at f of z, and this guy will go to the limit of f prime at f of z. All right, so let's look at the second proof. In the second proof, we want to apply the chain rule from just real analysis in the two-variable real chain rule, right? So, so let me name the f of z. Let me call it w for simplicity. And the chain rule from two real variables, what it says is that matrix, the derivative, for the composition, well, the composition is first is differential, and the derivative is the product of the derivatives of g and f, right, as matrices, right? Now, these matrices correspond to these complex numbers, and so the product corresponds to the product of those numbers, so which is precisely what we want, right? So we know that just the real chain rule tells us that the composition is differentiable, and this fact tells us that the derivative is actually corresponds to a complex number, meaning the function is complex differentiable. Now, the same sort of chain rule holds if we're plugging in not a holomorphic function, but a function, a real differentiable function of one variable. So basically, it's this path. So we think of this, gamma, which is just a function of a real variable, right? In some real interval a/b, right? Now it's complex valued, so I can write down the real and imaginary parts of gamma. I'll call them alpha and beta. And then the derivative, well, one way to write it, as a common way to write it, I mean, it's a function of one variable, right? So it's just the standard one variable real derivative, right? Now this could also be interpreted as a 2-by-1 matrix because it's a function from R to R2. So you should really be thinking of basically a column vector, right? So that's what it could be, right? That's the derivative. As a, if I think of it as a derivative of a function from R to R2. All right. So if we have an open set U, a gamma that goes into U, right? This path, it's differentiable at T, right? And F is complex differentiable at gamma of T. Then the composition is differentiable, real differentiable in this case. Now, it wouldn't make sense to say complex differentiable. The composition is now a function of a real variable, right? T, right? So it's real differentiable just as a function of one real variable. And the derivative is what it should be from the standard chain rule. So the first proof you just follow in the same way. It's essentially exactly the same, right? You just don't think of one of the variables as being complex. Now the second proof is well, maybe slightly different. Not totally different. Depends on how you write it. What notation do you use? I mean, again, right? Let's call this gamma of T, let's call it Z, just so that I don't have to keep writing gamma of T, right? So then the real chain rule gives us this guy, right? Just like before. This is nothing different, right? And now this df of Z corresponds to multiplication by f prime of Z, and the gamma is the 2-by-1 matrix, which is represented by gamma prime, which is this number, right? So it's precisely, that's what it is, right? That's what the derivative is. So it just works out, right? So the result follows. So all right, so let's go quickly through some basic, very basic results. If I have two holomorphic functions and I add them up, I get a holomorphic function, and the derivative is the sum of the derivatives, right? The same for products, right? You have the product rule. You also have the quotient rule, right? So it's enough to just think of 1 over G, right? Now, of course, that can only be holomorphic on this set where G is not 0. But once G is not 0, then it's holomorphic, and the derivative is exactly what you think it would be. That is just exercise. You just adapt the real one variable proof for all of these. It's kind of do the obvious thing. It's maybe the multiplication and the division is slightly more complicated than the addition, but they're all kind of easy. Now, one thing that maybe we should note is that this is an open set, so this makes sense to call it a holomorphic function, right? Because this is really the inverse image of the open set, C minus 0, right? So the inverse image of an open set is open. Therefore, this is an open set. All right. Now, using the product rule, we get power rule, right? So for any non-zero integer, including positive, negative, whatever n, we get the following following proposition. If we take z to the n and we differentiate it, well, that is holomorphic, right? And we get the derivative that we expect. Therefore, a polynomial, any polynomial is, well, we've already seen that it's holomorphic, but now you have, a nice formula for the derivative, right? Rational functions, again, holomorphic by the same, you just apply the previous proposition. You have these polynomials are holomorphic, therefore the quotient is holomorphic, well, wherever q is not 0. And again, that's just an exercise. Now, let's mention another exercise. Mentioning a whole bunch of exercises. This one relates to a previous side remark. So let f be just this function defined on the entire complex plane, from the complex plane to the complex plane. Let it be 0 at 0, and at all other points, let it be e to the minus z to the minus 4. And so it looks maybe a little mysterious, but once you start working with it, you'd figure out why that's true. Now, it's an exercise to show, and you can use all the previous, all the things that we've done today, and the fact that the exponential is holomorphic that you've proved in an exercise last time, you can show that, well, all these guys exist at all points. You have to do the origin separately, but they do exist at the origin, right? And they satisfy the Cauchy-Riemann equations. But f is not even continuous at the origin, right? It's really wild. It's sort of, somewhere goes to 0, somewhere goes to infinity. It's really wild. So, the key is, it is not real differentiable. It's not even continuous. It's not even bounded. It's very, it's a very wild function. But it's definitely not not differentiable, right? Real differentiable, right? That's, and therefore not complex differentiable either, right? So, all right. So next time, what we're going to look at is Wirtinger derivatives. And so those basically give you another way of looking at the Cauchy-Riemann equations in a sort of more natural way, maybe. All right, so that will be next time. So see you then.